The next our speaker is one of top Ukrainian users doing experiments in DESI. She will present talk on recent results obtained in P16 line in DESI. Larysa Khomenkova from Kyiv.
From Ложкарёва Institute.
Ложкарёва Institute. Double affiliation. So yeah. Today is Ложкарёва Institute of Semiconductor Physics.
Did you see presentation?
Yes, we see and we hear you.
But not in the demonstration mode.
But not in the demonstration mode. I will change. Sharing. And now I hope you can see. Yeah? Is it okay?
Yes, yes.
I just move this. Okay. So I would like, first of all, to thank organizing of this conference and this workshop for inviting us to speak about our recent results. Actually, we got them in tight collaboration with DESI researchers Oksana Chukova and Evgenia, who helped us a lot last time in July. And I would like to say that there are a lot of people who was involved in this work. And besides researchers from Ложкарёва Institute of Semiconductor Physics and DESI from Hamburg, Germany, we have also collaboration with Ukrainian universities and Ukrainian research institutes, and also some kind support from our former colleague from France. I would like it first to say thank you for Nephew Projects who helped us this July to come in DESI and to do all the investigation what we planned with Dr. Ludmila Barkovska. And we got really good results. We completed our previous study and already published paper on the manganese-doped magnesium oxide co-doped with lithium. This paper is accepted in Optical Materials Express X, and I hope that it will be published very soon. It's just only now in the proof correction. And I will speak today not so much about physics, but to show the possibility which we got when we joined this P66 line in DESI, and would help us to get some answers on our questions, but I guess we got more questions that we will look for answers in the future. So actually we are working with the multi-component materials, and one of them is zirconium oxide. This is wide bandgap material, and it has very diverse applications. First of all, it appeared in different forms like crystals, ceramics, films, and powders. And due to good optical thermal properties, optical properties, electrical and chemical, it has huge amount of applications. Actually, it's considered for high temperature resistance and anti-corrosion coatings, chemical sensor, for catalysis, for thermal barriers, for microelectronics, and for medical applications. You know, in this industry, they have we use a lot. And the last time, it's also considered as alternative energy sources like solid oxide fuel cells. And in all these applications, the most important question is what is the effect of the crystalline structure, and how crystalline structure will govern the future application. Usually, zirconium oxide appeared in monoclinic crystalline phase. And to get tetragonal or cubic phase, we can go either to very high temperatures and to have this crystal transformation, but upon cooling, we will get back monoclinic phase. And to stabilize these two phases, they have much advanced properties than monoclinic one. They have high dielectric constant, they have high ionic conductivity, and they are more stable for different corrosion effects. And to stabilize the structures, we need to use dopant. Usually, yttrium considered is the most useful dopant, but in the recent years, different subvalent dopants also considered. For different applications, the doping should be with different content of dopants, and sometimes it's used several dopants, like so-called co-doping. For instance, if we use subvalent dopants, the required charge compensation for dopant will give us formation of additional oxygen vacancies. And exactly these vacancies play a role as stabilizers of tetragonal or cubic structure. In our work, I will address the effect of doping with subvalent elements, first of all with yttrium and co-doping with copper, scandium, cerium, or with europium, and to show the variation of structural and optical properties of zirconia. We concentrated our efforts on this study to get information about possibility to monitor the properties of doped zirconium oxide materials, aiming their various applications. First of all, in microelectronics as alternative dielectric to silicon oxide, then as alternative energy sources and in catalysis. Just a bit history. It's as known from the history, it's possible to stabilize tetragonal and cubic phases via two effects. Otherwise, one of them is grain size, to manipulate with grain size, and due to high ratio between surface area and volume of the grain size, due to surface tension can be achieved stabilization of tetragonal or cubic phases. In this case, it can be about, the grain sizes of zirconium oxide can be about 10 nanometers. And if we will not use annealed in very high temperatures, like high 1,000 degrees Celsius, the stabilization will be perfect. Other way is to dope with subvalent ions. As I told, yttrium is the most used. Usually, if we dope with about 3 or 8 atomic percent of yttrium, we can get tetragonal zirconium oxide phase with the grains about 40 nanometers. And if we add more yttrium, we can get cubic phase with the same grains sizes, or we can get tetragonal phase in the larger sizes. It's about 70 nanometers. However, there is two questions. First of all, what's the effect of additional doping of other elements on yttrium dope materials? And other question, whether we can monitor their properties using mostly optical methods. In our previous research we concentrated on the yttrium and copper co-doped zirconium oxide. The aim of that research was to produce powders for catalysis. And we actually saying in advance we got good catalytical activity, but there were a lot of efforts to get insight on the incorporation of copper, interaction with yttrium, and the effect of annealing temperature on the structure and other properties of these materials. Usually we use different structural characterization like X-ray diffraction and electronic spin resonance to get information about crystalline structure and about surface complexes on the grain of zirconium oxide. As you can see from the left image, it shows the evolution of X-ray diffraction taken from the powders doped with yttrium and copper, about 3 mol of yttrium and 8 mol% of copper oxide. And you can see that until 800 degrees Celsius, the spectra is not vary, so we know that our materials was stable with tetragonal structure, and annealing at 900 degrees Celsius and higher resulted completely in the transformation of tetragonal structure to monoclinic. If to take a look on the peak of X-ray diffraction peak at about 30 degrees, it usually showed the variation of tetragonal to monoclinic phase and vice versa. And you can see that at first we have a shift in higher angles that say about copper incorporation inside the zirconia grains. Then at high temperatures after 700 degrees C, it goes to the opposite direction. This means that we have transformation of tetragonal, losing tetragonality and formation of monoclinic zirconium oxide. And at the highest temperatures, we have a bit backward, and we detected in both monoclinic zirconium oxide and cubic zirconium oxide. And if we have a look on the electronic paramagnetic resonance, we got information about first formation of copper entities, copper oxide entities on the surface of zirconia grains, then its incorporation and in this decreasing in this intensity incorporation grain inside in volume of zirconia grains, and at higher temperatures we see dramatic transformation of the signal. And this signal exactly correspond to formation of copper on the zirconium side, and these defects appeared only in monoclinic zirconium phase. So this means that if we have such defects in our materials doped with copper, we definitely know that we have monoclinic phase. If we combine the results on the zirconium, on the X-ray diffraction and electron spin resonance, we can say that we have possibility to monitor transformation of crystalline structure and to follow from tetragonal to monoclinic transformation. And we see the formation of specific fingerprint, will say us that monoclinic phase exactly exists. Taking into account these results, we also used different optical methods to get insight what happened with our materials. Usually to know information about oxygen vacancies, we should follow the ultraviolet absorption. This is exactly in the range between 250 about 350 nanometer, and this is signal corresponding to formation of oxygen vacancies, different oxygen vacancies. The signal from 600 to 1200 nanometers, this is related to copper, different phases, either isolated copper or crystalline copper oxide located on the surface of the grains. If to compare the photoluminescence, we discovered that when we got exactly formation of monoclinic zirconium oxide, we had a very bright in luminescence in the green specific range, and it became high as higher copper content, and it became high as higher transformation between tetragonal to monoclinic phase. Combination of optical characterization allowed us to suppose that we can use such doping or properties of copper to see where we are. So if we have monoclinic phase formation or not. And measurement of luminescence spectra and electronic paramagnetic resonance definitely say us the way how to control. But there is a question, was it possible to follow this ID for other materials? First of all, we take care about zirconium oxide doped with scandium and cerium, because these materials are considered mostly as alternatives to yttrium doped zirconium oxide in terms of their application in solid oxide fuel cells. To work for work of these fuel cells, the amount of oxygen vacancies should be high. And the higher amount, the higher ionic conductivity and the higher electricity that we can get from these oxide fuel cells. In our work, we take into consideration 4 different powders. So this is produced, 2 powder, black lines show the powder produced in Ukraine. All others produced in different companies in USA and Japan. And we take care about the optical properties. Exactly, we check first whether we have oxygen vacancies. It's just to say you in advance that the amount of oxygen vacancies in yttrium doped zirconium oxide is quite low in comparison with scandium and cerium doped oxides. And actually, the most powders were nearly the same chemical composition. They are different in some impurities that we are not able to control. And all the powders had cubic structure, as it was shown, for instance, in this TM image for specific powders. But when we start to see what happened with optical properties in terms of their light emission, we discovered that they have completely different luminescence. We cannot exactly bring together yttrium doped materials with undoped materials and with scandium and cerium doped. So all the different dopants produce some different defects. And for us, it was also point whether we can control them. And what discovered we at first, when we just measured here in DAISY photoluminescence under 160 nanometer excitation, we observed that for 3 powders that have nearly the same chemical composition, we have completely different spectra. If powder 1 and 2 are more or less similar, the third powder was completely different. We have specific emission band appeared in this powder. And checking annealing treatment for the same powder, we discovered that for one type of powders, we have decreasing in intensity. For another type of powders, it will be increasing in intensity. And in this case, it was some question where we are with structural properties, and should we or can we use optical characterization for checking our properties of zirconium oxide. First of all, we did annealing treatment at different temperatures and check about their transformation in optical absorption. You can see that the higher annealing temperature or high sintering temperature, we have higher contribution of different oxygen vacancies. And this is band quite high. Indeed, as we know from application in solid oxide fuel cells, we measure conductivity of these materials. Indeed, for samples annealed at 1,400 degrees Celsius, the conductivity is the highest. And if we check structure of these materials, we can see that annealing at 1,400 degrees Celsius results in formation of the huge or large grains. So it was 2 questions. What to do with such variation of photoluminescence with different excitation wavelengths and how to control. Thank you for development of luminescent mapping in P66 line. And this July, we took exactly these good maps. In these maps, we have in the horizontal direction variation of excitation wavelengths from 140 nanometers up to 250 nanometers. And in the vertical direction variation of the photoluminescence wavelengths from 300 nanometers to 500 nanometers. These 2 maps are plotted in nearly the same way. The intensity of the scale bar is the same for all these maps. And if you can see on these maps for sample annealed at higher temperature, we have more bright emission, which appeared at 350 till 500 nanometers and excited by mainly from the 140 nanometers to 160 and from about around 210 nanometers. And for the samples annealed at low temperatures, we have nearly similar picture, but photoluminescence band is a bit shifted to the low wavelengths, and excitation band is shifted to the high excitation wavelengths. And actually, this difference showed us that if we will run each time just to check for specific photoluminescence under specific excitation, we can lose some information. Definitely, it's better to use such mapping, and it's give more answer on these questions. Our assumption was that we have such difference in intensity and increasing in intensity due to higher sintering and higher temperatures, and probably all the defects which are provided this emission. This is definitely oxygen vacancies, or they are B vacancies, and they are located in the grains with large sizes. Additional possibility to check crystalline quality of the material is to dope with some markers. Actually, europium ions are really very good for using as a marker of the crystalline structure because their emission is sensitive to the crystalline field. And for our case, we use a very low amount of europium to see whether we're able to excite these rare ions through excitation through matrix absorption or band-to-band absorption. And sure, we can excite it directly, these ions. And if to have a look on these two maps, we see that we have really very good emission of the host exactly appeared between 200 nanometer till 300 nanometers and in the excitation mode, and we have really good emission of europium ions. But if to check all photoluminescent spectra taken under different excitation, this spectra extracted also from this mapping, and it was measured additionally during usual measurement as many people used. And you can see that we have some specific excitation between 200 nanometer to 250 nanometers. In spectra are quite similar, black, red, and green one. And when we switch on the higher excitation wavelengths, we have difference in luminescence spectra. And if to check the excitation spectra for this band at 640 nanometers, you see that we have completely different excitation spectra. The blue one is mostly probable due to band-to-band transition is close to zirconium band gap. It's about 240, 250 nanometers, and some transitions appeared here. And for other bands, we have one broad peak, and it can be either transition from a cold charge transfer band from oxygen to europium 3+, or it can be also one type of oxygen defects, like oxygen vacancies that we cannot separate in this way. However, we can say that if we use band-to-band excitation, that is possible in our case only in DAISY for our samples, then we can definitely get emission from rare S ions via excitation through the host absorption. And just one slide to show you the variation of europium emission when it has very small amount of europium. It's about tenths of mole, 0.1 mole %, and when we have about 5 molar %. You can see that it's, I took two maps, a bit shifted in the wavelengths, but here you can see that in this left map, we see the band, the good emission from the host and red emission from the rare areas. But when we dope with high amount of europium, this is emission from the host is disappeared. It can be disappeared due to two things. First of all, it's already transfer all the excitation to the rare S ions. Otherwise, it can be also a possibility that europium doped dopant of europium also stimulates transformation from monoclinic phase to tetragonal or cubic phase. And this point needs some confirmation. Raman scattering spectra confirms this idea, but we need more structural characterization. So this is what I want to, and just one point that if we use europium dopant and if it's really stabilized, it was one point when we asked our colleagues, and they told that it definitely stabilized cubic and tetragonal structure with a high amount. And what is good, that it's possible to use such materials also for alternative energy sources like solid oxide fuel cells, and they have quite good electrical conductivity. So just to conclude my talk, first of all, I want to say that if we want to study wide bandgap materials, we need really advanced tools. For our luck, we were lucky that we were able to get the easy synchrotron, synchrotron facilities. And this is really, in my opinion, help us to get a bit and answers on the host-related emission and doped zirconium oxide. And what is interesting that for doping of several impurities, we have different photoluminescence spectra with samples with similar composition. This can be due to either impurity which we are not control, or it can be really due to larger grain sizes or variation of grain sizes, and that will affect the presence or the nature of the host defects. And it's possible to use rare as ions. For instance, europium is quite good. And if europium situated in zirconium sites, it demonstrates specific luminescence that can be used to see the contribution of different polymorphs, or it can favor monoclinic to tetragonal phase transformation of zirconium host. And I'm very thankful to Evgenia who helped us to use exciton emission maps, because it's really give more answers on the questions what we have. And we are not running for each specific spectrum. We can use these maps and to do analysis and actually to get insight on the luminescence mechanism. Thank you very much for your attention. And I also would like to acknowledge again the nephew project which helped us to come this July in DAISY and to complete the first trial of our investigation. Thank you a lot. Sorry for taking a lot of time.